Hello and welcome to ECMath. Today is going to be a very quick video reviewing the properties of logs. I'm assuming you've already seen some logarithms in another class. This probably shouldn't be your first go-around. If it is, you've never seen a logarithm before, I'd find a different video to watch. This one's going to go pretty fast. So what is a logarithm? Well, it's a thing that solves for exponents. Technically, a logarithm is the inverse operation of exponentiation. So we'll start with an example. If we have 2 to the 5th is 32, which is a true fact, then what we're going to write is the log base 2 of 32 equals 5. Now let's take this apart and look where everything went. The 2 is called the base, and that's the base of the exponent, and it also shows up down here, and that's called the base of the log. The 5 is called the exponent. And the whole point of a log is that it solves for the exponent. So the exponent appears on the other side of the equal sign when you're translating an equation. And then what is a 32? Well, in the exponential form, 32 is sometimes called the power. Like it's the 5th power of 2. So we could say that this is the power. But another word for it, when it's on the logarithm side, is the argument. Not like argument, I'm going to fight with you, but argument like input. That's a technical word that we use a lot in functions that means the input. So 2 is the base, 5 is the exponent, the log solves for the exponent, and the what was the power, or the result of the exponent, goes into the argument of the log. And there's this little switcheroo between the 32 and the 5. Let's be a little more official about this, maybe translating the other way. So if you have something like log base b of square equals triangle, just to, it doesn't have to be numbers, just to kind of get a sense of how this really relates, b is still a base, and it becomes the base of the exponent. Then the argument of the log goes to the other side of the equal sign, and what the log was equal to is the exponent. So when you transition this into an exponential expression, the exponent becomes, attached to the base. So what that means really is that a logarithm is an exponent, right? This is equal to the thing that becomes the exponent. So when we think about rules of logs later on, thinking about logarithms as exponents or related to exponents is really going to help us understand why the log rules are the way they are. Okay, so how do you see this in problems? The first type of problem you might be called on to do or might encounter is just having an equation with an exponent and needing to switch the form from log to base exponent or exponent to log. So this is already an equation, but we're trying to maybe solve for y. We don't know what y is. We can't, think about it, just puzzle it out. So all we would do is rewrite it as log 2 is the base, so we write base 2 down there. 13 is the power, so that becomes the argument of the log. And y is the exponent, so that's solved for over here. And oh my gosh, we've solved for y. It's log base 2 of 13. I don't know what that is, but we could figure it out at some later point. Now what if you have a spookier expression? So this one seems like, maybe we're trying to solve for m. We're trying to think about what do we do here? Well, it's a log expression, so one of the things you can do is just write it as an exponent expression. 2 is the base, so this is going to be 2. I'm going to write this out. 18 is the exponent, so this is going to say that 2 to the 18th equals the thing that was the argument, 2 to the m. Now, here's something cool. We actually are able to solve for m because we have this matching base on both sides. We can now say confidently that 18 is equal to m. So sometimes switching the form, even if it's complicated in expression, can let us solve for things that we couldn't solve for before. And that's one of the main values of logarithms, is that they let us solve expressions with exponents that we couldn't solve before. A really similar type of problem, but one that confuses students, is you might be asked to evaluate a log. And that's something that's like either of these two down here. And what's weird is that there's not an equation. It's like, what do I do when there's no equal sign? I can't switch the form. Well, I want you to think about that word evaluate as a command. It's telling you to basically think like a computer or a calculator and pretend that someone has typed this into your command line. You just have to give the answer. So one way to think about it is just to put a question mark over there, right? We're trying to evaluate this. We're trying to figure out what question mark is and then switch the form. So this would be in this form, 3 to the equals 1/3. Well, we know about exponents that must be -1. So this log would evaluate to -1. And if you're asked to give the answer or evaluate a log, you don't write this. That's not the answer. -1 is the answer when you're asked to evaluate it. Just what would that simplify out to? So, be careful about the type of question you're answering. Sometimes when you're evaluating logs, you can attempt to evaluate it, but you can't make any progress. So for example, this second one, log base 7 of 50, would be saying 7 to the equals 50. Well, we know that 7 to the 2 is 49, so it's probably a little bit more than 2, but we don't know what it is without a calculator. So actually, I would say this just evaluates to log base 7 of 50. This is the exact answer. Again, a lot of people mix up exact. Think exact means, oh, I need a lot of decimals. Exact means infinite precision. So sometimes with log expressions, when they don't come out nicely, you just want to leave them. But you could say this is, a little bit more than 2. If you had to, or you're, just trying to estimate. Sometimes you see a logarithm and there's no base visible, or it doesn't look like a logarithm, and this messes people up because they don't know what to do. So the first example of this is the common log. So when you see log without anything down here, you should infer that this is a base of 10. That's because we live in a base 10 number system. So a lot of our stuff is base 10 when you're doing computations. So if you're asked to do log of 10,000 here, what it's really asking is saying put a base down there of 10 and then ask the question 10 to the what equals 10,000. And since 10 squared is 100, 10 to the third must be 1,000, 10 to the fourth must be 10,000, so this would evaluate to 4. Another log you might see is something called the natural log. This is the log with base e. So log base e, we'll put an argument, log base e of x, is the same as natural log of x. So whenever you see something like ln of e squared, for example, you can think about this as log base e of e squared. And let's evaluate this. Well, this is saying e, that's the base, to the equals e squared. So this we can tell must come out to 2 because we have that parallel structure between the exponents when we have the matching base. So often you see ln and e kind of together in the same equation. You don't have to. We're going to use ln to solve log equations later without any e's involved. It's just a very popular log because e is a very popular base. And it's also very fast to write. So often doing calculus later on and math later on, you're really only going to use natural log. You won't use all the other ones, which is a little weird right now. All right, there's 2 main ground rules of logs that create logical log expressions. And the first one is you can't take the log of a negative. Let's just try. Let's do the log base 4 of -16. I know 16 is related to 4, so this would be saying 4 to the equals -16. If you look at that for long enough, you'll realize there's no way that you're going to take a positive base, and the base of an exponent has to be positive, and get a -16 there. So there's no solutions here. We can't take the log of a negative. The other thing we can't do is we can't have a base that's -0 or 1. So for example, we couldn't have log base -2 of anything, log base -2 of 8, because as we're saying -2 to the equals 8. Well, you might be able to do this, you might not be able to do this, but just as a general rule, we're going to say bases can't be negative. And similarly, they don't want to be 0, and they don't want to be 1. I'll leave those up to you to figure out why those don't make sense, but just turn them into exponential form, and it doesn't work. we're going to close with 4 properties of logarithms that you really, really need to know. Because you don't want to have to be switching things into log form all the time. Sometimes you just need to know a property and see how something simplifies. And the first property is when you have log base b, that is any base. So I'm just using b here to represent any number, positive, not 0, not 1, etc. But any number that's a valid base of 1 is equal to what? Well, let's just turn this into exponential form. This would be saying b to the equals 1. Well, why is that true? I'm going to put this in the y column. Well, the only thing that makes this true is 0. B to the 0 equals 1. So log base b of 1, no matter what the base is, will always equal 0, no matter what. So when you're doing a problem and you're simplifying, and you get down to something like log base 3 of 1, you don't even have to switch the base. I want you to just know, oh my gosh, that's 0. There we go. All right, what if we have a log base b of the same base? So we got this kind of matching situation. Well, let's turn this into an exponent. This is saying b, the base, to the equals b, the argument. Let me highlight this. This is the base. This one's the argument. But what does this question mark have to be? Well, this b on the right is b to the 1, so question mark must be 1. Log base b of b is always equal to 1. And this comes up also a lot, and people always forget to simplify this, and they lose points on it. Especially with natural log. Natural log of e is the same as log base e of e, and by this property that log base b of b is 1, log base e of e, or natural log of e, always simplifies to 1. Whenever you see that, it just becomes 1, and it then disappears from your expression. So these are 2 really useful properties when simplifying. The last 2 properties are a little more complicated, and they're called the inverse properties altogether. We inverse in the sense of inverse functions. Remember how we talked about inverse functions? You might have f of f inverse of x, and if those 2 functions are inverses, then you should get x out as a result. Well, the whole point of logs is that they're the inverse of exponents. So when you have a log and an exponent with the same base sort of nested within each other, they're going to simplify out nicely. So let's take a look at log base b of b to the x. Well, this is saying, I'm going to highlight again. This is the base, and this is the argument. So we have b to the equals b to the x. This is the b to the x from the argument. This is the b to the x from the base. Well, the question mark must equal x, so log base b of b to the x must always simplify to x. So if you have natural log of e to the 10th, instead of doing this whole dance of simplifying it to log form, this is just log base e of e to the 10. By the inverse property, this is 10. And that's how fast that should simplify. What if we had a b with a log in the exponent? This feels like you shouldn't be able to have that, but often you do get this. This comes up from time to time. And we do the same thing, except we're going to put it in log form. So in this case, b is the base here. And so we're going to say log base b, that's the base b, of so we're saying this is equal to question mark, equals, and then we're going to put the exponent on the other side, log base b of x. And again, we have that parallelism that, I'm out of colors. The question mark and the x are in the same spot, which means that this question mark really is just x. So if you have b raised to the log base b of that power, it just simplifies out to whatever that x was. And so say you have 2 to the log base 2 of pi. Ick, right? Nobody wants to evaluate this. It's irrationals sandwiched in irrationals. But because of this inverse property, we know that this is just equal to pi. And if we wanted to write this out, we could say that we could put this in log form, right? You know, that it's log base 2 of equals log base 2 of pi. Oh my gosh, it's pi. But we didn't need to do that because we already had the inverse property. So these all relate to the idea that logs and exponents are inverse functions of each other. So when you nest them together, you should just get out what you got in, what you put in. And then to close this out, we've kind of been hinting at it by doing natural logs and other logs. But all these properties apply to every base, not, log base b, what we've been talking about, but also common log, that base 10, and the natural log, base e. So there's nothing special about those other two. Don't get scared of them. That's it. All right, so I'm going to leave this up. That's a good place to write down all the log properties. You do need to know those and use those. They come in very handy. But that's it today, folks. Thanks for watching, and enjoy your homework, and I'll see you next time.